Okay, good morning. I hope you can hear me because I've had some problems with audio, so I had to rearrange my devices. And today we have to finish up with the conic sections, and then we shall see. Perhaps we can move on to the next topic already in analytical geometry. But our main task today is to finish up and have an overview in the sense of practice exercises, an overview of conic sections, all of them, circles, ellipses, hyperbolas, and parabolas. So first of all, we will start by having a look at what we did last time, as always, as most of the time. Please don't forget. Please don't forget to write your name in the meeting chat. Because if you forget it, then you are marked as absent. I know that there are some people who simply switch on the computer and then get lost and then show up at the very end, perhaps to write their name. So this is why I am reminding you and reminding you. And if you are not writing your name now, there's no way I count you as present from the very beginning. But now let's move on to hyperbola. So the hyperbola, as you remember, was the, there it goes. The hyperbola is the locus of all points in the plane for which the difference of the distances to the two foci is constant. That was the difference. For the ellipse, remember, the sum of the two distances had to be constant. For the hyperbola, is the difference. And part of the reason, or one possible explanation for the two branches of hyperbola, for the two pieces, is that it depends on which distance is longer. If distance to the right focus is greater than the distance to the left focus, then we are looking at the points on the right-hand branch of the hyperbola, and if it's the vice versa, then we are looking at the left-hand branch of the hyperbola. That might be one possible explanation. But we also had a look at a little animation that demonstrated how actually the sections, the shapes of the curves change depending on the inclination of the plane with which we actually intersect the cone. And so we had the standard equation for the hyperbola, the canonical equation. We assume generally that the hyperbola opens horizontally, that it is placed on the x-axis, so the real axis, the axis that actually intersects the hyperbola, is horizontal. And the distance between the two vertices of the hyperbola is called the real axis, the length of real axis. So the number a, which is the distance from the origin to the vertex, and that was, just a moment, could I do this? No, I could not. There was some option. Okay, sorry. And that's the imaginary axis. We call it imaginary because the vertical line, y-axis, and the segment from minus b to b on the y-axis has seemingly nothing to do with the hyperbola itself. It does not intersect. It doesn't give us any segments on the hyperbola. So how do we know that it has any meaning? But of course, once we investigate the asymptotes, the two slanted lines, the dashed lines in that diagram, we understand that the segment B and the segment A both play a role in actually drawing the asymptote. So the eccentricity, the focal distance C, as always, the connection somewhat different from the ellipse. So the ellipse has a sum in the equation, but the difference in the formula for the c square. The hyperbola has a difference in the equation, but the sum in the connection in the equation for the c square formula. Eccentricity is, as always, the distance of the focus to the center C divided by the main, in this case, the real axis, the horizontal axis, half axis A. and asymptotes that were not present in the case of the ellipse or circle, of course, but for in the case of hyperbola, we have two lines that the graph approaches. So just to remind you what we did on Monday. And of course, we had this other hyperbola. So using the same frame, that is, using the same A value, using the same B value, the same rectangle, and the same asymptotes, and evidently the same C value, we can also draw a hyperbola not opening horizontally, but also opening vertically. We call it the conjugate hyperbola, the connected hyperbola to the canonical one. And the equation is very similar. The one exception is that we had -1. We had -1 in the equation instead of 1. Or we could actually swap the two terms on the left-hand side and leave 1 on the right. And now, a reminder, just like in the case of ellipse, A is always on the x-axis. B is always on the y-axis, which means now the names change a little bit. The semi-imaginary axis is now horizontal because it does not intersect the hyperbola. It is the imaginary segment that plays a role, but it doesn't have anything to do directly with the hyperbola. It doesn't give us any segment on the hyperbola. And B, or 2B as the full real axis, now is the real axis or semi-real just for the half of it, the B value, because it actually really is a real axis for the hyperbola. It really intersects the hyperbola or the transverse axis. And then the foci have the same C value, the same distance from the center, but in this case, they are on the y-axis. I'm not sketching anything in these diagrams now because this is what we did on Monday. We went through all this on Monday. This is simply a very quick review, a very quick revision of what we did. And so the formula for C is the same, and the eccentricity, yes, we have to use B for eccentricity now. We have to use B for the eccentricity now because B is now the semi-real axis. And for the eccentricity, the importance is the relation between the focal distance and the semi-real axis. Now the same asymptotes and the same focal distance. So we had quite a few exercises for the hyperbola. This is, I do believe, was this where we stopped? It's very possible that this is where we stopped actually. So at this point, we considered the parabola. So equidistant, all points in the plane, equidistant from a given point and a given line, and we call the line the directrix. And the canonical equation, that is the main equation of the parabola, was this. That actually applies to the situation. This applied to the situation where the parabola opens in the positive x direction. I will go through this the same again, so you don't have to hasten to copy this right now, those who were absent on Monday. So the illustration is this. So now I am just repeating things. So the equation, the canonical equation, y squared equals 2px, where we notice an interesting thing, that we do have y squared. It is still a second order curve, but we do not have an x squared here. So that's the interesting moment for parabola. So this is how we can recognize that the equation should describe a parabola, but not something else. So now let's do, okay, there we are. And okay, I'm sorry, at the beginning we need to use some darker pen so that I can write in the diagram. And that would be here. So F has coordinates b half, so b half 0, b half 0. It's on the positive x-axis, as you can see, the focus. You also see that the vertex of the parabola is at the origin of coordinates, and that the directrix has equation x equals minus p half. It's a vertical line parallel to the y-axis. So the noteworthy thing is that the distance between the directrix and the focus is p. And the other interesting thing is that the equation, however, has the double p. It is 2 times p. It is 2 times p. And this means that we have to be careful with these numbers. The coordinate of the focus, p half, the distance between the directrix and focus, that is full p, but the number you see in the equation will be 2p. So not to confuse these things. Where we have p, where do we have 2p, where we have p half. So basically the p is the least used of all those, because we mostly use the coordinates of the focus and the equation of the directrix, and we use the equation of the parabola, but we don't use the number p by itself. However, it is a characteristic of the parabola. It is the characteristic that actually gives us the exact shape. That is, how flat, how fat, how wide, or how thin this parabola actually is. Depends on the number p. But we use, for practical purposes, we use the number p half because it's the coordinate of the focus, and we use the number 2p because we see that in the equation. So that's something interesting. Unlike ellipse and hyperbola, where you see the characteristic numbers immediately in the equation, a and b, you basically understand what a and b are from the equation immediately, and they give you those segments in the curve, in the coordinates. The 2p, well, it's not much different. A squared from which you get a, or 2p from which you get p, and p half perhaps. But that's a slight difference. You feel the difference from the hyperbola parabola. Interestingly, hyperbola and ellipse. Interestingly, hyperbola and ellipse have, in some sense, more in common than the parabola. That's an interesting moment. However, of course, the parabola could sometimes open to the left, in the other direction. We are used to the idea that p is the distance. Because p is the distance, between directrix and focus. And that means p must be positive. That means we assume that p is positive because it's a distance. That means that for this, we have the equation y squared equals minus 2px, because this equation will make sense only for negative values of x. The first equation, that would be this one, makes sense for positive values of x only, because y squared can only be positive, or 0 in the case of vertex. In the second case, the second equation makes sense only if x is negative, because p is distance, it's positive. So to get the positive y squared, x has to be negative. So this might be an explanation that's why this parabola, that's how we can know, that's not why the parabola is like it is, but how we can know that the parabola opens to the left. And the focus evidently has the negative x coordinate, negative p half, and the directrix would be positive p half. So that the directrix would be x equals p half positive, unlike the first case. And then we have these two extra parabolas that are opening not sideways but or down, like our normal functions from school mathematics, like our normal quadratic functions. So this means that x and y, in a sense, change places. So number 3, if we see x squared equals 2py, if you divide both sides by 2p, you basically get the standard parabola from school mathematics. Y equals 1. Please close your microphone. And from this, we could even think, we don't usually do that, but we could think y equals 1 over 2p times x squared. If we divide both sides by 2p, we see it's the regular parabola times some number. A regular parabola times some number. So opening upwards, or if we want it to open downwards, we need a negative coefficient at x squared. So that would be x squared equals minus 2py, opens downwards. And the focus is, of course, at 0 and minus p half. And in this case, I should write down the directrix. The directrix is, in this case, horizontal. So the directrix would be y is negative p half. And in this case, the directrix is y equals positive p half, if the focus is on the negative y-axis. And last time I also mentioned, so this is number 4. And last time I also mentioned a way to tell which equation corresponds to which graph, or which parabola corresponds to which equation. We notice that one of the variables has a square and the other one does not have a square. So the sign can be changed only on the side that does not have a square, because square is always positive, which means the variable that does not have a square actually determines which way the parabola will open. If I have this kind of equation, I see x has no square, so it opens in the x direction, like in this as well. We know positive or negative from the sign. If I have a positive coefficient at x, then it will be opening in the positive x direction. If it has a negative direction at x, then this parabola will open in the negative direction. And similarly with y, because y does not have a square, it will be opening in the y direction, and because in this case to be positive, it would do it in the positive y direction. And in this case, because we have a negative coefficient at y and y has no square, it will open in the negative y direction. So this would be the connection from which we can basically memorize and recognize how exactly which equation for the parabola should we choose. So generally, when we have a choice, we use the canonical equation. In other words, today we will have an exercise, we'll have an example where we may choose how to place parabola in the coordinates. For practical purposes, that actually is something very important. How to make our calculations as simple as we can. And that would be, let's say, using the canonical equation, because typically the canonical equation makes the most sense. It is the simplest of equations, in the sense that it gives us the most information about that curve. That's why we call it canonical, because it's a standard in some sense that it gives us the standard information about this curve. And now on to exercises. So we saw this applet last time, but now we are moving on to how to do this in practice. So let's just see how things work out. Y equals 4x. So we look at this, we understand that this parabola will be opening in the positive x direction, because we have a square equal to 4x without any square. This means it should be opening in the positive x direction. We also know that the canonical equation of a parabola means that the vertex of that parabola is at the origin. Don't forget to label the axis. We also know that 4 actually equals 2p, which means p is 2 and p half is 1. This means that the coordinate of the focus on the x-axis will be 1. So the focus has coordinates 1, 0. When we mention coordinates of a point, when we are asked to find the point or give the coordinates of the point, remember we have to give both coordinates of a point because one number is just a number. A point must have two coordinates. And so also the directrix will be evidently x equals minus 1. So the directrix, I will use some different color to make things more interesting, hopefully. So the directrix is a vertical line passing through the point minus 1 on the x-axis. This, and the parabola itself has vertex at the origin and opens to the right. The exact shape, yes, we should probably find some more points if we want to sketch it accurately. For example, this is 0, y squared is 4, sorry, if x is 1, y squared is 4, that means y is plus minus 2. Well, I guess I have done it more or less accurately, right? When x is 1, it does look that y is plus or minus 2. So I get a couple more points so that I basically can estimate how flat or how thin this parabola will be. Okay. Hopefully, so far it's clear. Let's move on and let's make it a chalk once again. So x squared equals minus 2y. Evidently, the coefficient is minus 2 and y is without the x. It opens evidently in the negative y direction. So I start by looking at that equation and deciding in which direction should I actually sketch the parabola, in which direction it opens. Now I see that evidently P is 2. Remember, P is positive, so the minus sign only tells us that we are opening in the negative direction. So, sorry, it's 2P, not P. 2P is 2 because we always have this 2P in the equation, which means P is 1 and P half is what we are interested in, is 1/2. And so the parabola should open downwards, y and x and the origin. So the directrix will be horizontal at 1/2. So supposing this is 1, then this is 1/2, and the directrix goes horizontal. So the directrix will be y equals 1/2. The focus will be 0 minus 1/2 because it's on the negative y-axis. This will be the focus then. And the parabola should be opening downwards. And again, if we like, we can actually find some values. For example, if x is 1, or if x is 1, then y should be equal to minus 1/2. So if x is 1, this is 1. Observe the scale 1, then y is minus 1/2. So if x is 1, then I have 1 equals minus 2y, and y is minus 1/2. So it should be there. The point should be there because this is minus half. If x is minus 1, we still have the same point, of course. So again, I can estimate the flatness of the parabola. My sketch is not very accurate, but at least I can estimate things. It looks the same flatness as the first one because I have changed the scale, as you can see. Here, the scale, this segment equals 1, this segment equals 1. But if I go down to the second picture, the scale, the segment equals 1 is this. This is 1 unit. So the parabola looks approximately the same flatness, the same shape exactly, but that's because I changed the scale. I'm looking at this at a different scale. So if x is 1, then y values are, then the y value is minus 1/2. This is only for the sake of more accurate sketching, nothing else. So in principle, if you are in a hurry, you can sketch just, let's say, a little bit more sloppily, but still, however, especially in the homework, you should be very careful when graphing. Try to do it as accurately as you can, because homework is where you have time. Next. Okay, if we exchange the two sides in C, you get y equals x squared. That's our classical parabola. But now we are looking at it not from the school mathematics viewpoint, not from functions viewpoint, but from analytical geometry viewpoint, which means 2p equals 1, p is 1/2, and p half, in which we are interested, is 1/4, which means the focus, it will open upwards, as we understand very clearly. The focus will be on the positive y-axis, so it will be 0, 1, 4th. Okay, if this is 1, say this is 1, then 0, 1/4 is somewhere here. The focus will be somewhere there. And this is the origin, and this is the y-axis, and this is the x-axis. And the directrix is y equals minus 1/4. The number will always be the same in this situation, except that the signs are different. B half is B half. And so the directrix is at the same distance below the axis. So interestingly, the directrix, of course, never touches the parabola. That's an interesting moment. However, it plays a role, as we have already seen in several occasions. Color. Let's make it orange. Okay, so for this parabola, we know very well y equals x squared. That means if x is 1, y is 1. If x is minus 1, y is 1. So we can sketch the classical parabola from school. Y equals x squared, the classical standard parabola. And we see that the focus of this classical standard parabola is actually quite low, close to the vertex. It's not at 1. We might think, oh, the standard parabola, the focus is at 1. No, the focus is not at 1 from the vertex. Distance 1 from vertex. It's 1/4 from the vertex. So that's worth noticing. Now we have D, which will evidently open in the negative x direction. Negative x direction, because we have x times minus 6. It will open in the negative x direction. And so we can see P is 6. We ignore the signs when we are 2P. When we are looking for P, we ignore the signs, because remember, P is the distance. Therefore, we must take the positive number. So P is 3, and P half is, let's say, 1.5. So the focus will be on the negative x-axis. That means at the point minus 1.5. Okay, I did it a bit too quickly. Minus 1.50, and the directrix will be x equals positive 1.5. So now let's suppose this is 1, this is 1. Let's mark the scale on the axis. Actually, marking the scale on the axis when you graph when you plot curves or graphs of functions, it's imperative. You need to set the scale on the axis so that we understand where each coordinates actually are. We can understand the coordinates, we can understand the numbers. And of course, as always, the vertex is at the origin. Now let's see. The directrix is at x is 1.5. So that would be here. We have the directrix. There it goes. This is the directrix. And so now we will mark the focus on the other side. This is -1. So -1.5. That will be the focus. This is the origin. And yes, if we like, we can find some values if, for example, where do we get a nice square if x is 6? That doesn't work very well. So if x is 1.5, if x is 1.5 or -1.5, if x is -1 and 1.5, then y squared is 9 and y is actually 3. So basically, focus is a good point in this case where to evaluate the y value. If we have x equals -1.5, y squared is 9 and y would be equal to 3. So this and -3, 1, 2, -3. So if x is -1.5, then y squared is 9, so y is positive or -9, and we can actually graph it. So vertex and this point, so that this parabola, as you can see, is flat-ish, approximately like that. So evidently I should have graphed this a little bit more smoothly like this, but that's how we go about graphing a parabola if we have the canonical equation or any of the other three variations of the equation. So the first task is the first two tasks. The first task would be to discover the direction in which we have to draw the parabola, and the next task is to discover the value of p half, the coordinates of the focus and of the directrix, vertical, horizontal directrix, and where exactly the focus is. And then when we have marked the focus and the directrix, remembering that the vertex of the parabola will be, in this case, it will always be at the origin, we can sketch the parabola. Of course, for all curves, for all these curves, what is possible? It is possible that these curves are shifted away from the center. It is, of course, possible to have the ellipse somewhere away from the center, horizontal or vertical, or sometimes even slanted, which we will not consider. The parabola could be shifted away from the center. The hyperbola could be shifted away from the center, as is the circle. You know that the circle is based on its center coordinates along with the radius. We will discuss these situations a little bit later. And now the other way around. Write the equation. So this task does not require any sketching. This task does not require any sketching. However, we might make just an approximate sketch so that we understand what's going on. So first of all, the focus will be on the 0, -8, negative y-axis. Negative y-axis. So the focus is on the negative y-axis. The directrix evidently on the positive y-axis, but this means that, remember that this is then negative pi half. So pi half is 8. That means pi is 16, and 2 pi, which we need for the formula, is 32. And so in this case, because this parabola, the focus is here, that means the vertex is at the origin. We have no options. It does open downwards. And in this case, I'm not even trying to sketch it precisely and accurately. This is simply an approximate, sloppy sketch just to give us an idea of how the parabola lies and how we should write the equation. So evidently, y will be with a negative coefficient. This negative coefficient is 32, so minus 32y, and of course x squared on the right-hand side, on the left-hand side. Because if we have p, if we have p half from the focus, we know where the focus should be. We can deduce in which direction the parabola opens, so we can actually very quickly find 2p. You could also do a shortcut. Of course, you can understand that you have to multiply this by 4. You don't have to do p half times 2 is p, and then times 2 again is 2p for the formula. You can multiply by 4p directly, of course, if you know the focus. And you can take the coefficient from the equation, divide by 4, to get the coordinate of the focus immediately, of course. I'm doing it a little bit more slowly so that you have time to think about what is going on here. So the next one, 6, 0. The focus would be on the positive x-axis. Positive x-axis. So this means the second, I will use a different color simply for us to be able to tell the difference. For C, so focus will be here. The parabola evidently will open in the positive x direction. So we see that p half is 6. So 2p is 4 times greater, obviously 24. And we have to use it in the positive, meaning we have positive x-axis. So it's y squared equals 24x, opening in the positive x direction. So in fact, we can write the equation rather quickly. We multiply the coordinate, the non-zero coordinate of the focus, by 4. We look at the focus where it actually is situated. So we understand in which direction the parabola should open, and we can write down the equation. So basically 3 things to consider. And the last one, I will take it in orange, for example. So here we see, okay, p half is 2, which means 2p for the equation is 2 times 4, it's 8. Minus 0 means it's on the negative x-axis. So the parabola will open to the left in the negative x direction. And y squared equals minus x. Please keep your microphones closed. Akhil, please. Okay.
Okay, ma'am, I have. Yeah.
Because to hear if you say something, I have to keep my volume onto 100%. It's really, really loud, and it evidently will echo back to you. It's not the best thing. Okay. So here we go. How to, knowing the focus and knowing where the vertex lies, we can actually write down an equation, the canonical type of equation for the parabola. The canonical situation is, I remind you, when the parabola opens horizontally or maybe vertically in the positive negative direction. More generally, we consider the canonical situation in the positive x direction, but the other 3 situations are also allowed. So in the canonical situation, it's basically very simple. In a non-canonical situation, that would be a bit more difficult. Now, next, extra information. So in this case, the vertex is at the origin, the vertex is at the origin, so x and y, the vertex is at the origin. And we have 1 point. And symmetrical about the y-axis. This means it will open either up or down. Symmetrical about the y-axis. So it opens either up or down. Passes through the point 6 minus 2, okay, 6 and minus 2. This means that this parabola would be opening downwards. It cannot open up. It cannot open up. Let me take the eraser for this half. Doesn't look so nice. It opens down because we see the y coordinate is negative. We should have understood it immediately. Now we do have this point A with coordinate 6 minus 2. And now we have to write the equation. So of course we understand that classically the equation should be opening down, that is x squared equals minus 2py opening downwards. We don't need to know p itself. We need to find the equation, which means for the sake of writing down the equation, we only need to find this constant. After that, we will be able to find, okay, the focus is there, the directrix is that line. It's not required at this moment. The only thing that is required is the equation. So what we need is actually to know what is minus 2p. So in this case, as usual, with all curves, if we know one point, we can put the coordinates of this point into the equation and figure out the rest. So x squared will be 6 squared equals minus 2p times minus 2, which means 36 is minus 2p times minus 2. Divide both sides by minus 2. We have minus 18 is minus 2p. So this is what we put in the equation. I don't care what p is, although yes, I see p is 9, p half is 4.5, so 4.5, so 4.5 would be the y coordinate for the directrix. But in this case, we only need the equation, so I'm writing x squared equals minus 18y, and that's it. And that's it. I don't need pi itself. I need minus 2 pi as the constant in the equation. So this would clarify, hopefully, the general idea. If I know the general form of the equation, if I know what the equation should look like in principle, and I know some points, I can put the coordinates of that point or points into the equation and get a new equation to find out the unknown parameters, the unknown constants for that equation. What else do we have? Okay, it's the same point C, 6 minus 2, but in this case, symmetrical about the y-axis. This is not a specific case from your lecture sheet exercises because I give it from myself so that you see what the difference is. What is the difference? The difference is evidently, it still passes through the same point, 6 minus 2, but now it's symmetrical about the x-axis, which means it's opening to the right. Again, a very inaccurate depiction, but it doesn't matter. So in this case, the equation should be y squared equals positive 2p times x. 2p times x. In this case, I would say minus 2 squared, because I put y in there, equals 2p times, and x is 6. So actually 2p equals 4 over 6, or 2/3. And my equation is y squared equals 2/3 times x. So a completely different equation from the previous case. So this information, evidently, this information is important because it tells us in which direction this parabola will open. So because on that direction, the equation, the shape of the equation, the form of the equation depends. All right, we are through half of the lecture. Very good. Now, another one. This is very typically something parabolic. Remember I told you about the very nice property of the ellipse. The property of the ellipse was the thing that actually is in the base of the so-called whisper galleries. That is, if you and your friend stand in the two foci of an ellipse, and one of you whispers, then actually the property of ellipse is such that from all the directions in which your sound travels, it reflects from the ceiling and goes straight to the other focus, which means you might be whispering very quietly, but the reflections from all points of the ceiling will go exactly to your friend and focus, so the sound will come at your friend. Your friend will receive sound from many directions at the same time, and that will amplify that sound. So something that he wouldn't be able to hear directly across the distance, because of this amplification, he hears very clearly after that reflection. So the parabola has another interesting geometric property. The parabola has an interesting property such that if we have the focus of the parabola, then if we, for example, have why the satellite dishes are parabolic? Why do we have a satellite dish like this, and then we have the receptor, the receiving device up there? That's because when we receive in the same direction, basically from the satellite, a weak signal from the same direction from the satellite, the signal always reflects to the focus. Always reflects to the focus. Again, the same situation, it gets amplified because many weak signals coming from the same direction, parallel to the axis, will reflect into the focus. And similarly, when we need a transmitting antenna, according to the laws of physics and geometry, what happens is that if we transmit from the light source, for example, a parabolic mirror, then the mirror reflects the light from every point of the mirror. The light is reflected in the same direction. This is the reason, for example, for the lighthouse, the beacon, the lighthouse lamps are inside parabolic mirrors. That explains why we have these parabolic mirrors in the lighthouses, and they have actually not one mirror but a system of mirrors, so that actually this light gets amplified quite enough. And this is also the reason why we have these parabolic dish antenna dishes for satellite vision and satellite communications all over the world. And also, there's an interesting thing. For example, in the First World War, there are still some constructions like this found in the coasts of England. Built from concrete, of course, walls like this, parabolic walls. That's from the First World War, because the First World War and the Second World War, because the people on the coast needed to know when to seek shelter when the enemy ships or enemies airplanes were approaching, and somebody was always sitting at the focus of this wall, and even when normally the sound of the plane or the sound of the ship couldn't be heard normally, then if the sound came into this parabolic mirror, it reflected the sound to the focus, and actually so the observer, the lookout, the scout, could hear the sound of the motors even when the aircraft or the ship was far, and normally the normal people outside that wall could not hear it. So this is a very, very useful property for a parabola. And now we have this task: a parabolic mirror, diameter 80 centimeters, depth 10 centimeters. So what we understand about this dish is that this distance is 80, and depth, this distance is 10. And the question is, where should we put the light source? Where should we put the light source? So what we will do, we will make the canonical equation of this parabola, that is y squared equals 2px. So we will place this parabolic mirror in the canonical situation, that is, let's place it so that the vertex of this parabolic mirror is at the origin of the coordinates. We have this parabola. Okay, we have this parabola. We understand that at the point 10 centimeters, x is 10, the height, the point on the parabola has evidently height 40, because the diameter is 80, so evidently 40 and minus 40. In fact, what we have is, we have the coordinates of a point on the parabola, coordinates 10, 40. And that's where we can find the value of 2p. In fact, what we need to find is p half for the focus. The focus is at p half. So we put the coordinates of a point, a known point on that parabola, into the canonical equation. We find p, we divide it by 2, and we can find where exactly should the light source be placed in the mirror, so that for example, the lighthouse can operate normally. So we see y squared, that would be 40 squared, equals 2p times x squared, that's 10 squared. So this means that we have p equal to 1,600 divided by 200, and that is actually 8. That's interesting. It's 8. And did I do it correctly? 40 centimeters, 10 centimeters, squaring for 1,600. Yes. 100, 200, yes. 8. So p is 8, and p half is 4 centimeters. That means the light source should be somewhere here inside the mirror, deeper inside the mirror, not outside like we have, because our satellite dishes are generally quite flat, because that's quite enough. That's quite enough, and we know that the transmitter or receiver is quite out of that dish, quite a distance out of that dish, because that's enough to be able to receive the signal quite clearly. So in this case, we need a powerful light beam, and that's why evidently the mirror is bigger, so that the reflecting surface is comparatively bigger. In the satellite dish, you see the reflecting surface is comparatively smaller. That's enough. That would be enough. In this case, we see that comparatively larger reflecting surface will result in a more powerful light beam. All right, so that was the last problem about parabola, pure parabola. Now we have some more exercises. Okay, all right, I drew the system of coordinates myself. I forgot that I had actually already done it before, because I did it for the last time for Monday, and I forgot that I already had this. Yes, that's right. That's a very good question. I did not have to take the square of 10. That's where you are completely right. That's my mistake. Thank you for noticing. This was not a square. This was not 200. So this is 80, not 800. That's correct. So I was doing quite a lot of giving you a lot of strange information. So actually, no, it had to be 40 centimeters out of the out of the mirror. Not 4, but 40 there. I was thinking it was not something that I remembered. 4 was not quite enough, and I was starting to weave some strange stories. You are perfectly right. Thank you for noticing. I was just going by inertia, without thinking. Okay, y squared, and then I write x squared as well. I wasn't thinking. I'm sorry. So it's 40 centimeters. It's 40 centimeters. Okay, I'm giving you a little bit of time to correct my error in your notes. So not this, not square. So we had a square, no square here, no square here. So this was not 200, but simply 20. So this was 80. So this is now 40. This is now 40. This is the correct point. All right, I think that was it about parabola, just parabola, and now we have combination questions. So this is from the file 3.3.5a, which is only exercises, combined exercises about second order curves in general, and also lines. So in this case, now if we look at this first exercise, line y equals kx. If it's simply the equation of a line, we understand that this line passes through the origin. It should pass through the origin in the system of coordinates. If x is 0, y is 0. Doesn't matter what the k value is. Now the circle, we have to think about the circle. Line intersect the circle twice. So in a way, it would be possible to solve this actually without any sketching. But because this is analytical geometry, we will in fact deal with the sketch so that we understand what is going on. So first of all, we take this equation of the circle and let's say normalize it in the sense of let's find the center, let's find the radius, and so on. So we will have x squared minus 10x. 16. Let's move 16 to the other side already. So for the complete square, to complete the square, we need to add 25. Because that way we will have x minus 5 squared if I have added 60 to 25. So on the right-hand side, I add 25, of course, as well, because 25 by itself, of course, was not present in the given equation. So if I add something extra, I add it to both sides. And then I have simply plus y squared. So plus y squared equals evidently 9, which tells me that the center of the circle is at the point 5, 0, and the radius of the circle is 3. So the circle would be, something like this. The center is at the point 5, 0, and the radius is only 3, so the circle does not reach the origin. The circle does not reach the origin. So this is approximately what it looks like. Now the line intersects the circle twice. That means the line looks something like this. Remember, it has to pass through the origin, definitely. Through the origin. So intersecting the circle twice means the situation is this. Tangent to the circle, that would be the situation like this, only one point in common. And non-common points with the circle, that's this, it's no common point. So 3 possible situations for the line and the circle. Of course, we did not really need the sketch because it's clear that a line and a circle can have 2 points in common, 1 point in common in the case of tangency, or no points in common. So why should we use analytical geometry? That's because we see that to find the common points, let's suppose, okay, we need to find the common points. This means I have to solve the system of equations. So the common points could be found by solving the system x square plus y square minus 10x plus 16 equals 0 and y equals kx. If we know k, we can find the coordinates of the common point, or maybe the system would have no solution if there are no common points, but we do not know the value of k. So what do? We still use it. We still take, okay, let's take y equals kx and let's plug it into the first equation. Let's pretend we are finding the intersection points. That's the whole idea. We are pretending, we are thinking of, okay, let's try to find those intersection points. And that would be x squared plus y squared is now k squared x squared k squared x squared, that's y squared, minus 10x plus 16 equals 0. It looks almost like a quadratic equation. Let's take x squared outside parentheses, then the total coefficient at x squared would be 1 plus k squared minus 10x plus 16 equals 0. And now all we need to see is, how do we know how many solutions this equation or this system has? If it has 2 solutions, then we have 2 intersection points. If it has 1 solution, we have 1 intersection point, that's the point of tangency. And if it has no solutions, then we have no intersection points. And so what happens here? Is that we need to determine the number of solutions. That is done, of course, by the discriminant. And the discriminant we know is b squared minus 4ac. In this case, b is minus 10. So we have 100 minus 4 times a. This is the a coefficient, 1 plus k squared. 1 plus k squared times c. C is 16. So now to simplify, we have 100 minus, that's 64, minus 64 k squared, and that is 36 minus 64k squared. That's the discriminant. And now all we have to see is, when is the discriminant positive? If the discriminant is positive, then the discriminant is positive, there will be 2 solutions, 2 intersection points. When the discriminant is equal to 0, then there's 1 point of intersection, that's the point of tangency. And when when the discriminant is actually less than 0, then there are no common points. So let's see. So 36 minus 64k squared intersects twice, is greater than 0. We have to solve this quadratic inequality. Today in elementary mathematics, we will deal a little bit more, we will talk more about solving quadratic inequalities, but in principle, we need to find the 2 critical points where this is equal to 0. So we would say that 36 is equal to 64k squared, or k squared is 36 over 64. So k is positive or negative 6 over 8, that's 3 over 4. So minus 3 over 4 plus 3 over 4. This is where the discriminant is 0. So in fact, we already have one answer. This is where the discriminant is equal to 0. So I can write down one answer. That is if k is positive or negative 3 over 4. This is already solved. The discriminant is 0 when k is plus or minus 3/4. Now we think positive, negative, the signs. So let's see. If k is very large, greater than 3/4, very large, anything larger, then this term becomes too great, too large. So subtracting 36 minus something very large will be negative. If I have k negative, but also very large absolute value like minus 10, or, well, minus anything further to the left than minus 3/4, then the square is still positive. The subtracted term is still too great, so we still have a minus. But if k is comparatively small, then 64 times k is small, so 36 minus something small would be positive. And so we see the circle would be intersected twice if k is between minus 3 over 4 and plus 3 over 4. Or we can write k belongs to the segment minus 3/4 plus 3/4. Then the line would intersect the circle twice because the discriminant of the resulting equation is positive. And no common points in all the rest of situations. That is, if k absolute value is greater than 3 over 4. Absolute value of k, remember what the absolute value or the modulus of a number means. It means the distance from the starting point, from 0. So evidently, if the distance of the number k from 0 is greater than 3 over 4, then the line has no common points with the circle. We see how analytical geometry might help us solve geometrical problems using pure algebra. We have to understand, we might think in terms of sketching, perhaps. We might even start thinking about what's going on there. We need to find the slope. We need to find rise over run or something. But in fact, we can see that a geometrical problem is solved by simply using a quadratic equation from algebra. Or rather, in this case, it will be an inequality. And as I said, later today in elementary mathematics, we will discuss algebraic inequalities, linear inequalities, quadratic inequalities, and other inequalities as well. Next, another one. A circle is given by an equation. A chord passes through the point M. And we know that M is the midpoint of this chord. So first of all, I will attempt to sketch something. So I will sketch this chord. Okay, almost straight line. This is the chord. Let's call it A, B. Let's say the center is C. The center is C. At the moment, we don't know the coordinates of the center, but we will get them. Point M is the midpoint of this chord. All right, midpoint. And we have the coordinates of M, and they are 1 and 3/2. And yes, we have to find the length of the chord AB. So how do we do that? How do we find the length of the segment AB? If we had the coordinates of the points A and B, we could do that. That's one possibility. Another possibility is pure geometry. Just if we have a look at the situation now, if we work with the equation of the circle, we can get the center, the coordinates for the center, and we can actually find the length of the radius. So I will now attempt to sketch the radius. Okay, this. All right, this. So in fact, from the equation, I can find the coordinates of the center and of course the length of the radius. And that would mean I have to rearrange the equation. X squared minus 4x, just like the previous case, very similar to the previous case. I need to add 4 to both sides. Add 4 because I want to get the perfect square. I'm completing the square. There it goes. Then we have to add y square. Y square is there, but no simple y, so I don't have to work with the completing the square. And minus 5, let's move the minus 5 to the other side. So what we have now is x minus 2 squared plus y squared equals 9. So the center has coordinates minus 2, 0, minus 2, 0. The radius is evidently equal to 3. Now, how does this help us find the length of the chord? In principle, we could also think we have 2 points with coordinates that we do know, so that would be a good idea to connect them. Now, there's a very important understanding required at this moment. M is the midpoint, all right, splits the segment AB in half. So what of that? So what? So what is that CM is perpendicular to the chord AB. How do we know that? That's because ABC is an isosceles triangle. So the word is isosceles. Isosceles triangle, that is a triangle that has 2 sides equal. Depending on how you were studying mathematics at school, you may or may not know the word isosceles, 2 sides equal. For those triangles, you might remember, if we draw a height, it splits the base into 2 equal parts. It bisects the base. So if we draw the median of an isosceles triangle, it actually is the height if it's drawn against the base. If we draw the height of an isosceles triangle, it is the median. It splits the base into 2 identical parts. So actually we have 2 right triangles. And I know the hypotenuse of such a triangle, of this one. I'm looking at this triangle, at the triangle AMC. It is right angled. It's a right triangle. So I know the hypotenuse AC. I can find one of the legs. I can find CM. I know AC, I can find MC. So the distance from M to C is the length, of course, of the vector CM or MC. Let's take vector CM has coordinates 1 minus negative 2 is 3, and 3 halves minus 0 is just that, 3 halves. I'm not transforming the number. So the length of MC, and I would say squared, because we will need the square. For the Pythagorean theorem, we will need the CM square, because we will be able to find a M square plus CM square will be equal to a C square. So we need a square, which means I am not writing the square root. It's simply 3 square plus 3 halves square, which would be 9 plus 9 over 4, which would be 36 plus 9 is 45 over 4. That's the CM square. I don't care how it transforms, because what I need is the square, and then we will be able to deal with AM. So now looking at this, so that's Pythagorean theorem. From that, AM is that something that we don't know. So AM square plus CM square, that is 45 over 4, equals AC square, that is 9. That is 9. So AM square is evidently 9. Wait. Too much. What went wrong? CM square and 9. CM square should be less. 3 and, okay, just a moment. Where did I make a mistake, or am I not making any mistake?
C is not -2, C is 2.
Oh, right. Because this is a minus, this is a plus. Thank you. So 2 minus 1 is actually, this is 1. So this is 1. So this is 1. So this is 1. So this is actually 13 over 4. Okay. Now I will do it in a nicer way. This is not, this is different, and this will be different. Okay. And this is 1, and this is 1. Okay. Thank you. This is 1. This is 1. So this is 1. This is 4 plus 9. This is 13 over 4. 13 over 4. So this is 9 minus 13 over 4. 36. 36 minus 13 is 23 over 4. So AM itself will be square root of 23 divided by 2, which means AB is 2 times longer, which is square root of 23. I hope I got it right. I'm not checking against my correct answers, correct solutions. I'm doing it on the spot. So I think, well, it was an irrational number. That much I do remember. So the rest is, as you say, arithmetics, a little bit of arithmetics. I understand that in many cases you would prefer to use a calculator and find the square root of 23 over 4, which is basically not necessary because in principle, this is quite enough. We can get an answer without a calculator. So if you like to use a calculator, of course, in the general mathematics, of course, calculators are allowed for numerical calculations, so that should not be a problem. Another one, canonical equations of the given curves, and to sketch them. So this is where we get a serious situation. So we have the canonical equations for the curves, like for the ellipse, for the hyperbola. The canonical equations are x squared over a plus or minus y squared over b squared equals 1, or we might have y squared equals 2px, the canonical equations, whatever. I'm not worried too much about which curve I'm thinking about, because these are general considerations. So remember what happens with a circle. If the circle has center at the origin, it has equation x squared plus y squared equals radius squared. As soon as I take this circle and move the center to some other point with coordinates x0, y0, take the same circle, move it by the vector x0, y0, by the way. We are moving the whole circle by a vector. We get an equation x minus x0 squared plus y minus y0 squared equals radius squared. So basically what happens is exactly the same thing happens if we move an ellipse or a hyperbola or a parabola to some new location. So we simply imagine that the center, the vertex, the center, let's say, is the point that was at the origin of our construction, moves to the point x0, y0. This simply means that instead of x, we will have x minus x0. Instead of y, we will have y minus y0, and that's it. And the general form of the equation will remain the same. So if I want to move a hyperbola or a parabola, it will become x minus x0 squared over a squared plus, if it's an ellipse, minus, if it's a hyperbola, y minus y0 squared over b squared equals 1. The size and the shape of that object remains the same. The greater axis, the smaller axis, or the real and the imaginary axis remain the same. The distance between the foci remain the same, and the location, the whole thing simply means that the object is just shifted. All points are shifted by that vector. And for the parabola, it would be y minus y0 equals 2b times x minus x0. If we shift one of the canonical things by the vector x0, y0, that means that the center, the origin, moves to that point, then what happens to the coordinates is this. The coordinates actually become these. Still, from these coordinates, we can still have an idea what this object is like. So we could, for example, we could sketch it in the regular coordinates with the center at the origin, and then think about moving it, or rather moving the system of coordinates in the opposite direction. So the general idea is this. I will now erase the rest to clean up space. To clean up space for what we have to do. And see what is going on with this particular task. What kind of curve would this be? So what we need to do is, in principle, as you have already probably guessed in these situations, what we do is we actually separate the perfect square. We complete the square. So we would have x squared plus 6x, evidently plus 9. I need plus 9, so I'm taking this, but I need to add 9 in order to get a perfect square. If I add 9 to one side, I will add 9 to the other side as well. Then the next part, so this is taken care of. Now minus y and plus y plus 4y. In principle, minus y is not a very good thing, minus y squared. It doesn't make a perfect square. So I will actually do it like this. To create a square, I will put it in parentheses. So minus comes outside. In order to combine it with 4y correctly, I now need to write minus 4y. Because my minus is already before the parentheses, opening the brackets, minus must become plus. So finally, for this, I actually need to add 4 in order to get the perfect square inside the parentheses, which means this minus 4 is actually already taken care of. I didn't need to move 4 to the other side. I see this minus 4 will become plus 4 in the parentheses because we have a minus in front. And so now I can write this is x plus 3 square minus y minus 2 square equals 9. Not really a circle because we have a minus there. We have a minus in front of the square. So if I had a plus here at this spot, then I would have a circle. but I have a minus. And we know that the minus sign between the two squares generally means a hyperbola. So in principle, I could have told you from the very beginning, this looks very much like a hyperbola because we have x squared with a plus sign and y squared with a minus sign. So this actually, judging by the equation, the general equation of a hyperbola, means that I should have a hyperbola because I have positive x squared and negative y squared. Now to get the canonical or almost canonical equation, I need to divide both sides by 9 because remember we always like number 1 on the right hand side. So I will have x plus 3 squared divided by 9 minus y minus 2 squared divided by 9 equals 1. So in principle, I have a is 3, b is 3. A is 3 and b is 3. That much about the shape of the hyperbola. And so what I will generally do is, first I will start by sketching this parabola as if the center is not at minus 3, 2, but as if the center is at the origin. So I am starting by sketching the hyperbola simply to understand its shape and its foci. So now I will erase the remaining additional work here because I need the space for sketching. This will be the last thing that we do today, evidently, because our time will be up shortly. So we will finish, probably we will be able to finish. Let me just check how much. Oh, we have one more. All right, so that last exercise, that's something that we can do next time. Not a problem for the sake of revision. And so now, going back to this, let's see, A is 3, B is 3. Okay, 1, 2, 3. And 1, 2, 3. Always mark some numbers on the axis. It's important because otherwise I will put my own numbers and say, no, you have a wrong picture. So it turns out that this will be a square. All right, not very accurate, but still something. So the asymptotes now, the asymptotes are going like this, like this. The asymptotes are going like this. Now, what about the foci? The c value, the small c value. Remember, c squared is a squared plus b squared for the hyperbola. That would be 2 times 9. So c itself is 3 square roots of 2. So 3 square roots of 2. 3 square roots of 2 is 3 times, it's 4.2 or something like that. So approximately here, the focus number 1, focus number 2. Now I can sketch my hyperbola using this information, and I will do it accurately because this will be my main situation. This will be my main sketch. I wanted a different color. In fact, I wanted the ink color something different. Okay, let's make it yellow as always. So this is the vertex. This is the vertex of the hyperbola. And the hyperbola goes. Okay, I didn't get the ink color change. So this would be something like this. The hyperbola, it's not a very good sketch. Sorry. Not a very good sketch. So this is not the hyperbola I need yet. Okay, I'm sorry, I'm at this point, my sketching skills on the black tablet are not very good. So supposedly we have sketched this hyperbola. I will highlight it to make it more clearly obvious that this is what I mean at the moment. Okay. Oh, my tablet is skewed. That's the reason. Okay. And so now we need to do something. We need to do something about this move. So in principle, I should move this hyperbola so that the center of the hyperbola goes to this point, to the point -3, 2. That would be somewhere there. I should move the center to this point, -3, 0. The problem with it is that it would be very difficult to move the whole hyperbola and sketch it once again. It's enough trouble to sketch it for the first time. So instead of moving the hyperbola by the vector -3, 2, as indicated by the new center, I will move the coordinates in the opposite direction. So in principle, I will move the coordinates in the opposite direction. So move system or coordinate axis, let's write move axis by the opposite vector, 3 -2. Instead of moving the hyperbola in the direction -3, 2, I will move the coordinates, the axis, in the opposite direction. That's a trick that is quite often used in mathematics when we have to sketch and move a rather complicated, perhaps comparatively complicated curve. We do it by simply moving the coordinates. Yes. So we move the axis to 3, so 3 units to the right, 3 units to the right. This will be the new y-axis, and 2 units down, that would be 2 units down, that would be somewhere here. So this will be the new x, okay. This will be the new x-axis. This will be the new axis, x prime. And this will be the new origin. This will be the new origin, O prime. So now I can understand how my hyperbola will actually lie. It will lie so that the vertex of the right-hand side is on the y-axis, as we can see. It will be there now, and the whole thing will be moved. You see, if I move the axis in the opposite direction, it's like as if you are a small kid sitting in a train and then saying to your mom, all right, the trees are running backwards. We are sitting in a train, so, oh, see, the trees are running backwards behind the window. So this is approximately the situation. Instead of moving the train, the hyperbola, we move the trees back. We move the system of coordinates in the exact opposite direction to which we wanted to move the hyperbola. So the movement goes in the opposite direction, but we move the axis. So that now, with respect to these new, the orange axis, we see, oh yes, the center has moved by -3, 2. The center really has moved there. Although what we actually did was move the system of coordinates. The frame of reference has been moved, but at the same time, we can perceive it as if the hyperbola has moved to the correct position now. So this is how we generally deal with these translations. This translation, that is a shift by a certain vector. Okay, what is this? All right. That's something to do with my devices, I think. All right, this is where we finish. For today. So I will see you in half an hour for elementary mathematics. People who are consistently not attending the elementary mathematics count with big trouble. And for the rest, so for the people who do not need elementary mathematics, I'll say goodbye till Friday. The rest of you, those who do take elementary mathematics, I'll see in 25-30 minutes. And a reminder, I promise to remind in every lecture This weekend we change the time. This weekend we change the time. So if you are in Riga, nothing bad happens. Just remember to check that your clocks that are not digital, not electronic, not online, check that they are turned 1 hour forward. Your computers, your phones will do it automatically. And those who are not in Latvia and do not change the time for summertime, recall that because we are moving our clocks forward, the lectures starting from next week will be 1 hour earlier for you. And for me, let's say physically, yes, of course, I will have to wake up a little bit earlier than I normally used to do it. So that's a reminder about the time change. The analytical geometry test will be after the Easter break, so the next end of week. We are missing actually 2 classes. We are missing Friday and Monday, the beginning of April, because of the very short Easter break, the Easter holidays in Latvia, which are bank holidays, Friday and Monday. That is, all the state offices are closed. So officially a free day. And after that, we will have the 3rd unit test. That was an announcement. And for now, I'm saying goodbye to those whom I see not earlier than Friday, and see you in a few minutes to those who come to elementary mathematics.